Okay, so as I said, this week is spatiotemporal models. To start out, I guess I'd like to stress that there's so many different ways that you can do a spatiotemporal model. So first of all, there's the whole universe of sort of nonlinear spatiotemporal models, and I'm leaving those out essentially. So, basically any data generating process, you can, any kind of real world, continuous time, continuous space process you could think of as a spatiotemporal model, or like an individual based model, you could probably represent as a spatiotemporal model. And so leaving out the whole nonlinear world, the world of nonlinear spatiotemporal models, and just thinking about kind of linear smoothers, kind of like we've been doing so far, there's a bunch of different ways you could do it. So I usually think of kind of this categorization where you could include or not include a spatial effect, and then you could have a temporal effect that's you could leave out a temporal effect. Well, okay, so a space effect is sort of the marginal effect of space. The temporal effect is the marginal effect of time, and we'll see notation for this in a second. And then the spatiotemporal effect is sort of the interaction of space and time. And so you could have the spatial effect or not. You could have the temporal effect and have it be, or leave it out, or and if you include it, it could be independent among years or smooth across years in some way. And if you have a spatial temporal effect, well, you could leave it out, or you could have it be independent or smooth across years as well. And so, if you think about this in terms of notation for the MGCV package of GAM, it's a 3x2 cross, or 18 models. Yeah, thank you. That's great.
No, it helps. Thank you.
Yeah. So this is sort of notation that the MGCV package uses. So I don't know how many people here actually use the MGCV package, but it's sort of a different, there's this, I think it's, does anybody know this, is it like Pinheiro and Bates who defined the kind of R syntax for linear models?
No,
it's kind of deep in.
I found the paper before.
If you refine it, email me. It's sort of some of those early. I thought it was an S, and it's sort of like in the prehistory of R. But people have kind of used this sort of notation to define models. And they kind of add complexities to it. And this is sort of the version of it that MGCV uses. And I just want to make the point that when you talk about spatiotemporal models, even leaving out nonlinear models, there's a lot of different ways to set it up. So, if you have no temporal effect, no spatiotemporal effect, and no spatial effect, it's obviously just it's just an intercept, which is represented by this C cache input response, tilde1 being has an intercept. If the temporal effect is independent, you put in a factor of t, and it means that basically you've got an intercept for every year. Let's see, smooth temporal effect. So yeah, S of t in a GAM world is a smoother on t, or like I think the MGCV package calls it, it says S for spline, I think, I'm not sure. And so, you end up having to get into this pretty like hoary kind of vocabulary, where if you want a smooth on your temporal effect, you put 1 plus S, comma, in parentheses t, and then if you want an independent spatiotemporal effect, you have to put S, X, comma, Y, by equals factor t, which basically in MGCV land means that you got a smoother on coordinates, spatial coordinates X and Y, but it's separately estimated for every level of factor t. Whereas you could also do a smooth spatiotemporal smoother, which is just a spline at X and Y and t. Getting in MGCV land, you can also get into this sort of discussion of whether this smoother by default is isotropic, I believe. So what it means is that, and we mentioned this vocabulary briefly, but haven't talked about it too much. Well, in theory, it came up in the last lab as well. So isotropy means that the decorrelation rate is the same in every dimension. And so if you've got a smoother, for instance, if you've got a smoother s, x, comma, y, it means that you decorrelate if you go 10 units in dimension x or 10 units in dimension y. That's the same correlation because they're decorrelating at the same rate as you move in those coordinates. And that could plausibly make sense for spatial coordinates like in UTM if you're measuring meters in both dimensions. It starts falling down when you've got latitude and longitude because if you're north, if you're in the northern hemisphere, 1 degree latitude is fewer kilometers than 1 degree longitude. And it really falls down when you start doing x, y, and t because time is measured in totally different units in space. So, for instance, in this model, if you rescale t from being years to being days, you would get a totally different fit in your model in a way that doesn't really make any sense. I don't know why you justify using days or years as a priority. But because it's assumed to be isotropic, because it's assumed to decorrelate at the same rate in all dimensions, you would have a decorrelation rate in units per meter, say, in x and y coordinates, and per day in t coordinates, and then there's no reason to think that would be a good smoother. So in theory, in MGCB, you could get even more complicated. You could start putting like a tensor spline, which is sort of one that has kind of like geometric anisotropy, like we started talking about in the lab last time. Well, it was in the slides of the lab last time, where you could estimate a different decorrelation rate in every dimension of your smoother. So if you do a tensor spline in MGCB, it would estimate a decorrelation rate in the x direction, and a separate one in the y dimension, and a separate one in the t dimension. Anyway, and finally, you can start, you can put basically everything in the model where you've got a marginal effect of space, a smoother on x and y, a smoother on time, and a smoother on the interaction of space, time, and year. And if you try to run this in MGCB, I think I've got an R script, I think, in the materials for this week where you can try to do that. I think it ends up being pretty slow. So, any questions? Or I don't want to get hung up on the notation, but I just want to point out that all of the same conceptual stuff we've been talking about apply when you start using kind of CAN packages, but it's kind of, it's kind of harder to tell by the notation they're using what it's actually doing.
So then avoid GLM, TMB.
I don't know. Yeah, my goal would be that, people can build their own TMB code. And so, personally, I always trust building my own version more than a CAN package. It's kind of nice when you can build your own and then corroborate that the package is doing what you think. If you can't match them, then there's a problem. There's probably a problem with there's some kind of problem you need to figure out.
Do you have examples of some of these in this lecture?
Examples of some of these configurations. No, this is all I'm going to talk about at MGCB.
Okay.
Like I said, there's an R script in the week 7 lecture directory that has a index model in MGCB, I think. I haven't looked very closely at it.
Just kind of thinking about like when and why to include these different sort of like nestings of things. Like, is it the kind of thing where you're like in a regression context, well, if I have this like 3-way interaction smoother for X, Y, and time, I also want the lower order terms? Or is it the kind of thing where if I have a factor in there for time, then like all of that variability will be in the smoother for time, and so I don't want those? Or does that just depend on your data?
Totally, yeah. I think that basically every one of these could be useful in some particular case, and yeah, I guess that's the other reason I put this up, is to start getting people thinking about why you'd ever justify one or the other. I was gonna, the pivot I was gonna do was that, an index standardization model I've defined as independent temporal effects with a spatial temporal effect that's also independent. So I've been calling this one an index standardization model, and I'll try to explain by the end of the class why this is an index standardization model like none of the other ones. But, you know, like when we've done climate, you know, like I did a paper trying to look at distribution shift. In that one, we did put a smoother across time. So, you know, sometimes I do this model, the bottom in the second column, if I want to interpolate across time. And so, you know, you start quickly getting into this sort of discussion of when each of these models is appropriate. And some of the principles worth keeping in mind, I think. So like Elizabeth, you started saying like, it's probably only good to put it in interaction when you've got the marginal effects. I think that's sort of a good starting point, and that's a property that this middle of the 3x3 cells on the bottom that I call the index standardization model has. Sorry, I can find my mouse. So this one is the one I call an index standardization model and has that principle that Elizabeth talked about where it has the marginal effect of time and the marginal effect of space, and then it has the interaction. Just to think a little more, so if this one's the one I call as an index standardization model, but Ole Shelton, our paper from 2014 that I showed originally, had this one that has an independent temporal effect, no spatial temporal effect, and has a spatial effect. And so why would I not want this one relative to the one below it? All else being equal, any thoughts?
The time trend is very by location.
Yeah, exactly. So this one has the additional, spatial temporal effect that varies independently among years. And so in fisheries land, that represents sort of interannual variability and distribution. So if you only do this one, which we published in 2014, every year is sort of, density in every year is just a fixed amount, proportion higher or lower. And so if you look at the statistics of distribution shift, like we'll look at later, that model will never generate any distribution shift for your population. And so it's kind of useless for detecting climate impacts on distribution. It also, a lot of fish show distribution shift, so it just seems like a good starting point to include that ability.
So for an index standardization, if you had something like the, an index like the ENSO effect, would you use the first, the top equation? And then if you had like a survey that did a grid index where space and time were both important, you'd use that middle one?
Yeah, so I'm not sure what you mean about ENSO. I definitely agree with the second part of that.
Okay.
Maybe we should take a step back, and I've got a slide in a bit about kind of defining what I mean by index standardization. So let's ask the first part of that question again later.
Okay. I think I just meant like more of a one-dimensional
Totally.
index that's not really space dependent.
Yeah, well, all right, this one I guess would generate, like, you would have a spatial effect, and then you could look at each year, whether it's higher or lower, kind of uniformly. And so, yeah, if you wanted to extract like an annual index of some spatial process that you want to assume a priority is as a distribution, I guess that top one would make more sense. Yeah.
Going off on the side here, but with these spatial temporal effects, if you assume like that, like with the middle one where both are independent, or you get, how do you predict then?
This one.
Yeah, how do you project that forward? Do you like average out between all?
Totally.
Yeah.
Yeah, so for instance, like I've been doing a paper where I want to forecast distribution, do short-term forecast of distribution.
Mhm.
And so this model, the index standardization model, by design, but by design, it has no structure on the intercepts, and so there's no way to forecast it. The intercepts are fixed. And so there's no way to generate a predictive distribution for any year that you don't have data for. And so if I want to do forecasts, I instead use a smoother on the spatiotemporal, and I also put a smoother on the intercepts. And so like my short-term distribution shift forecasts are done using this bottom right one. Yeah. So again, I mean, we can start kind of mapping out different cases where each of these different, I mean, we're kind of all looking at the kind of complicated ones. We're kind of looking at this bottom 9, but I think basically a lot of those in the bottom half of this could all be useful in some cases.
Should the middle one have an SXY term?
This middle one. Oh, sure, probably. Yeah. Sorry.
Okay,
It's,
then that answers it.
yeah, sorry about that. Yeah, cool. Yeah, looks like the rest. So these, I'm not seeing anything wrong offhand. Okay, so today we're gonna talk about that spatial index standardization model. And then in the lab, we'll talk about the spatial Gompertz model. So putting a smoother across space-time and year, but using a tensor spline. So okay, so so now we finally get to it. So what do I mean by index standardization? I'll come back to the sort of public health link in a bit. But.
Some measure of relative abundance that you get rid of effects that are due to your observation process rather than the actual population process.
Totally. Yeah. So it's a way of generating an annual index, and we usually do it by aggregating across space in some way, and we also set it up in a way that it filters out, either other sources of variance that we're not interested in. So like a lot of times we have Bessel effects where we contract vessels and they have some variation, and we can filter out that variance to have a more precise index. Or we can put in covariates like, I don't know, like the hook depth or something that might change systematically over time, and so we filter out a potential source of bias. So those are the reasons it's useful. And the link to public health actually is just this general issue of kind of 2-stage models. So there's somebody in biostats who actually is an expert in this and has just a totally different lit than we talk about here in UW. But I understand that, it makes sense that, public health and a lot of other fields have the same issue where, they might do, you might have a country that, I'm trying to think of how they do this. Like you might have a country that has, wants to figure out education rates, for each city, and then they've got, clustered sampling within schools within city, and then within a school they've got some panel design where they follow individual students over time. And, basically, it's just really complicated to analyze this sort of multi-level sampling design. And so people across a bunch of different fields, I think, have kind of developed these multi-stage models where like they've got a panel design of individual students over time. They use that to back out that student's sort of, gains per year and a trip, while filtering out teacher effects like people do now with kind of a teacher evaluation. And they look, they use the average teacher effect as a measure of the school. And then they look at schools across the city to look, to roll up to kind of educational quality of the school, the city level. And then they aggregate across that to a county, and then they just use the county measure of like educational attainment as a covariate in some model predicting, the health outcomes from educational attainment. So, almost always when we have, complicated data sets, there's all this statistical processing that happens as you roll up from our observation level up to the level that we actually usually think about. You know, you might have a demographic model of, you know, changes, you know, as an economist, you might want to fit an instrumental model, you know, instrumental variables model to how educational attainment over time affects public health outcomes. But what you're treating as data is actually some rolled up analysis from lower level sampling. You know, so anyway, so there's this guy, Sazalai, I think, here at UW, I don't know him very well, but who's done some kind of analytical work about, you know, bias variance trade-offs and these sort of lower level statistical analyses that go into a higher level model. The textbook example of this in fisheries is like a surplus production model. So we'll have a model where we want to fit biomass, so I'm using beta because I want to use Greek letters for all variables and Roman letters for data. We have beta in every year modeled as total biomass. We've got a production function G that might be like a, you know, Schaefer or Fox or whatever production function that represents production of fish biomass in excess of, you know, natural mortality. And then we've got an exploitation rate, F, being the fraction of biomass that's caught by fishing every year. And then we've got a process error, epsilon. Epsilon gets a normal distribution to make this a state-space model, and we can put a distribution on catch. And complete the model by specifying this observation model for the biomass. So we have an index abundance B sub T that is log normally distributed around true biomass, which you don't observe, times a catchability coefficient that represents the proportionality, this proportionality between the abundance index and true biomass. So for fisheries people, this is sort of like the first model they ever really look at, but maybe not with in state-space version.
Super state space version.
What's that?
Super state space version with the distribution on catch.
Yeah, right. So we call this like explicit F parameterization, and it's way more stable for surplus production. People still are doing the kind of like 80s version where you just subtract off catch and that'll just fall over it.
Then how do you, anyway.
Yeah. You know, there's all these different kind of computational tricks when you get into state-space land. So it's kind of a shame that people haven't really kept up the notational changes and parameterization changes as we kind of transition to state-space models. It's hard to know where to look for those.
Wait, so CT is catch, right? Yeah.
Yeah, totally.
Okay.
In this case, like production occurs and then catch occurs and then abundance. Like, you know, if you wanted a continuous time version of this where catch is instantaneous at the same time as production, I actually don't think anybody's done that model. So there's still kind of basic research to be done for kind of bringing these kind of classic fisheries models into like the 21st century. But
Yeah, I remember asking Andre about this in 558, like why we just put catch, like in the models that we just use catch is the catch. And
Yeah.
he said people don't like it when you think there's error in catch or something like that. And
yeah, well, it's the West Coast style. We don't want to do it. Noel Cadigan has a bunch of work about treating C as a error, you know, a variable that's measured with error. And, you know, in the way, you know, the point I'm making right now is about how biomass B is rolled up from surveys, you know, in this kind of spatial temporal way. But catch itself is actually way more hard to model. So, you know, if you look at catch on the West Coast, you know, for rockfishes, we've got 3 states, you know, each one has port-side samplers, and the port-side samplers are subsetting total catch into different species, but it varies seasonally, and they're also, you know, so we actually are transitioning on the West Coast to each state having a hierarchical model that rolls up catch from field surveys. It's really fucking complicated, and nobody wants to think about it, but it generates, you know, errors that are huge. You know, these errors on catch are like 40%, or some of the small rockfishes, you know, we get it in catch time series that's like 3 times bigger, and then they still want to assume that it's measured without error.
So then with this state-spacey one, you just put that error from that hierarchical model directly into sigma C.
Yeah, we're really getting, I mean, by the end of it, I want to talk about a lot of what the point of the index standardization model is to make sure that these errors are independent. So this specification, the way we do it on the West Coast, we say that each index is independent among years. And if that wasn't the case, we'd have to put a multivariate normal and put in the joint covariance matrix here. Nobody does that for reasons I can talk about. But for the cache, our cache time series are like hugely autocorrelated because we'll only have like one study in the 70s that said that dark blotched rockfish was 20% of the complex of shelf rockfishes at the time. So every time we recompute our cache time series, it's not like it changes by 40%, it's like 1920 to 1960 increases, doubles, and so realistically, we need to start modeling autocorrelation in this cache if we're gonna do that right. We could get into kind of more details about it, but I don't want to take too deep on it right now. The point I want to make is that C sub t and B sub t are data represented with Roman numerals, and they're actually derived products from a statistical analysis, first stage statistical analysis. And the proper design for that first stage analysis depends on how you model it in the second stage model.
Just one question on that. Too.
Yeah.
And the idea that you can do that, so I feel like a lot of times we're like, oh, don't do statistics on statistics.
Yeah.
Like use data, but there's something about sort of like sufficiency, like you've got all the information there, so you don't need.
Yeah, so that's like exactly. And by the end of this, I'll try to show that the correlation matrix for viewing the index standardization model is like 0.001 correlation there. But, so that sufficiency argument applies. But, whenever people say don't do statistics on statistics, I just think they haven't actually dealt with data. Because, even our cache records, the area swept is, the product of, like a trace that somebody did on the boat and some net width measurements, and it's just mess all the way down. And we're doing statistics on statistics all the time. I just think the right way to do it is think about what impact the first statistic has on the second statistic. Okay, so the simplified version of this, I'll call, I'll say Ci on the left follows a negative binomial for this, in this case, where we've got an intercept, T sub I, and then a spatial effect and a spatiotemporal effect. And the spatial effect has this correlation matrix where we can generate that from a 2D AR1 process that's equally spaced, or the SPD method that we talked about in the lab last week. And then the spatiotemporal effect in every year is just the same, but with presumably a different variance. And maybe this correlation matrix also differs because maybe you have a different scale of spatial versus spatiotemporal correlations. And if you write this out, sorry, I edited this, but I must have edited the wrong version. I'm trying to use R for correlations. And then if you think about it, the spatiotemporal effect, if you vector it across years, it's just a Kronecker product of the within year correlation and an independent matrix across years. And this identity matrix is just falls out of the fact that each year is independent.
Can you repeat that?
Yeah, so epsilon sub t is a vector of that spatiotemporal random effect every site in that year. And so if you think about all of the years combined, I'm going to describe it as a matrix with rows equal to number of sites and columns the number of years. And if you take that matrix and turn it into a big vector by using the VAC operator, it's going to have a covariance matrix with dimension equal to the number of sites times the number of years. And as we started talking about, I think in week 5, you can generate that joint covariance matrix as a Kronecker product of two different matrices, one with dimension equal to number of sites by number of sites, and the other one, number of years by number of years.
Sorry, does that neck argument just take like the columns and put them?
Yeah,
over each
stacks
other?
them, exactly.
So the.
Maybe we started talking about it during week 6
Yeah,
lecture.
I think you guys talked about it at the week 6 lecture, because you mentioned it, I think, in the lab lecture, but I don't think the other one was.
Okay, yeah, sorry, I forget when. But yeah, so some of this notation, probably, some of you guys missed with the Pop Dive Fellows meeting. So we could come back, maybe let's come back to that at the next week's lab, and people can try to watch the work. I didn't know that the week 6 lecture was even available, and just uploaded it now, so I don't mind if people haven't seen it, but maybe just try to watch it before next lab, and we can ask questions then. But the point is that this vector has length equal to number of sites times the number of years, and so this covariance matrix has to have the number of sites times the number of years as a square matrix. And that's generated by this outer product or Kronecker product of a covariance matrix across sites and a correlation matrix across years.
So the sigma epsilon is the variation across time.
Yeah, and exactly. You only need the Kronecker product of 2 correlation matrices and then a single variance.
Right. So I was gonna say, there's no spatial variance in that final line?
Well, so the spatial correlation is this R for correlation. And so it has a single variance representing this kind of magnitude of spatiotemporal covariance.
So space and time. is-
Yeah, exactly. It's kind of the net effect of space and time
Okay.
stuff that's being modeled by the spatiotemporal effect is that sigma p.
Okay, I don't know why I thought it would be like separated out. I don't know if that's suitable, like a variance of the time and the variance of the space, since they're not correlated in the space.
Yeah, well, exactly. The way this model is structured, there's a spatial effect and a spatiotemporal. And so
Oh,
if you think it through, I think I cut a slide. Well, okay, so this slide says that the variance across space and time is equal to the sum of these 2 variances. But if you kind of do the math, you can see that the correlation for a given site across time is equal to the spatial variance divided by the sum of these 2. And so you could reparameterize this model. Instead of having a spatial variance and a spatiotemporal covariance, you could think about it as having a total spatiotemporal variance and a correlation, representing the correlation at a given site across time.
Cool.
Yeah. And those are identical, and this one just has a little bit better properties in terms of maximum likelihood estimation. Okay, so if you do this index model, I mean, we looked at this plot a long time ago, and it's, this is the default I do for index standardization where I plot it. So it has an independent intercept for every year, and it has an independent spatiotemporal effect for every year, but it also has a spatial effect that's constant across years. And so that constant spatial effect probably represents the fact that, Pollack has higher abundance in the kind of middle and outer domain, the kind of south and southwest portion of the eastern Bering Sea. But it also has the ability to show shifts in distribution because of the spatiotemporal effect. So the fact that this hollow out occurred in the 2008-2009 period is captured by the spatiotemporal effect. And then kind of general increases or decreases are caught in the intercept that varies among years.
I'm just wondering why you can assume that space and time are independent.
So, yeah, so.
Because you would think that time, maybe, say you had a seasonal survey,
Totally,
that last season would be more related to the current season
totally.
than to like 5 years ago.
Yeah, and so my claim is that you could get a better model, you could get a better fitting model, almost 100%, by fitting a correlation across time in that spatiotemporal effect. And model selection, like AIC, would probably indicate that model fits better. But if you do it that way, it's also modeling a correlation among years, and so if you had a steep drop off in one year, it would shrink it towards the year before. And what that essentially means is that the index model is causing estimates to be correlated among years. And the problem with that is that we don't typically model that covariance in our index. Instead, when we fit the index, we assume that it's independent every year.
Oh.
And so we're intentionally using a model that fits worse, but when we get to the code, hopefully at the end of it, we'll see that the index model has the benefit that it actually has a covariance essentially 0 across years. So we're sacrificing fit to benefit, where the benefit is that it fits the assumptions of our second stage model.
Why don't we just have a better second stage model?
Yeah, so we just got an NPRB grant to build in a multivariate normal into SS3. There's just not enough good statisticians around to like do all the things that make sense. I don't know.
Huh.
Like it's low hanging fruit.
Mhm.
So yeah, let's come back to that.
Okay.
So I want to come back to this sort of discrete versus continuous data for a second. We talked about it in those early weeks, but we're finally kind of in a place to talk about it a little more. So zero inflated models are count data models, where you've got, a probability mass function for different discrete value counts. It could be, like when I'm talking with Simon Hay about Zika outbreaks, they might have data that's sort of the number per 1,000 or something. And if it's, actually taken from a larger portion, then you might have divided by something besides 1,000, you end up with non-integer values. But ideally, you'd have integer valued outbreaks because there's not half people getting Zika. But anyway, so if you've got counts, you can model it, this way, where the probability of 0 is from the probability mass function plus an additional portion of zeros. And in, there's a Martin 2005 paper where there's some that are true zeros that represent outside the proportion of the habitat, proportion that's outside of the habitat of the species, so that P sub I would be the probability of hitting a true 0. And then sometimes you get a 0 from the probability mass function, which kind of represents times when you're sampling in the occupied habitat, and you still get a 0. And so Martin wants to call those false zeros. I think that dichotomy doesn't really make that much sense, but people still talk about it. There's zero adjusted models, so kind of following this terminology that Jur uses a lot in kind of applied GLIMs. So a zero adjusted model is like a zero inflated model, except it just says the probability of hitting a 0 is P sub I, and then it just chops off from the probability mass function the component of that at 0. So it has a probability mass function from a parametric family, but it just chops off the 0 probability part and replaces it with a parameter. And it ends up looking like this. I'm kind of speeding up because I'm afraid we're going to run out of time before we can get the code. And then in terms of biomass, there's 3 different models that we ever look at usually. So one of them is the Tweedy distribution. Well, there's a conventional delta model that I'll come back to in a second. There's the Tweedy model, where you've got a Poisson count of numbers at a given site, where the intensity is equal to some numbers density n sub I. And then each individual has a certain expected biomass from a gamma distribution. And so if you sum across the biomass of each individual that you might have encountered, you end up with what's called a Tweedy distribution for the total biomass of that sample. So sometimes it's called it's a compound Poisson gamma. It's technically a Tweedy with a certain restriction on the power parameter. The Tweedy is a little more flexible, but this is where we use it in ecology. So the Tweedy, again, or a compound Poisson gamma arises in this case where sampling yields 1 or more individuals, 0, anywhere from 0, some count of individuals, and each individual has a certain biomass. And you're weighing the total biomass of that sample. There's the Poisson-linked delta model that I've been advocating because it's a lot faster than the Tweedy. It's just developed to have have the same moments as a Tweety, basically. Well, the first moments as a Tweety. So, you know, the probability of 0 is equal to the probability of 0 from a Poisson distribution. But caches follow a delta model where the expected cache rate is derived such that it also equals the same as the Tweety.
What if you don't have weight of the individual and you're just modeling counts
Yeah, so,
rather than biomass?
yeah, I think that just kind of, I mean, that's a restricted subset of this model, but it probably just won't fit well, is probably the answer. So the benefit, I don't think I actually do the count here, but the benefit is that all of these models can be set up to have the exact same number of parameters. So the delta model will typically have a linear predictor for a counter probability, P sub I. Here's, that's a low jet. And then it'll have a log length predictor for positive cache rates. The Tweety has a log length predictor for numbers density and a log length predictor for average weight for each individual. And then the Poisson length, you also set up the same way as the Tweety, where it's got a log length prediction for numbers density and a log length prediction for average weight. And so kind of my take is that the delta model is nice. I mean, somebody developed in Seattle in the 80s. It's been around fisheries for a long time. People are familiar with it. And I think the reason it was developed is that you can do just two separate GLIMs and multiply them together. So you do a logistic regression, you do a log normal model, multiply the products together, and you can just do it in a standard GLIM package. The Tweety is sort of something that statisticians are interested in. It's been kind of increasing attention in the 2000s. It's clear what the generative model is, and there's some kind of nice, it's nice having a generative model that's biologically motivated. You can also, there's some kind of ecological theory about the mean variance relationship and what that means. And it kind of automatically induces this correlation between P and R, so encounter probability and positive cache rate, that fits sort of macroecology expectations. So if you have a species that has, in general, abundant species are expected to have a wider range than rare species, and this certainly is what we see for marine fish. So if you've got a rare rockfish, like canary rockfish, it'll have like a 5% encounter rate in a kind of small core habitat off of, Oregon and Washington. Whereas if you've got an abundant species like Pacific hake, or let's say stablefish, that you encounter in 40 or 50% of every tow off the West Coast, it's also going to be distributed across the whole North Pacific. And, so that sort of macroecology rule is something that, people see across insects and plants and birds and mammals and fish. It's nice having a model that kind of automatically has that core expectation. But the Tweety is really computationally expensive. People keep trying to figure out shortcuts to do it, and all of the shortcuts are expensive. And so, so I'm advocating for the Poisson-length delta model that has the same structure as the Tweety, but is cheap to evaluate as a delta model. So taking the delta model as an example, do you want to ask something, Brent?
Wait, isn't this the zero inflated model though, not the delta?
No, so the zero inflated and the delta have kind of similar looking structure. I mean, you can write them to have similar structure. You can write both of these to also use like Dirac deltas, and there's a lot of different notations you can use, as I've seen when people write up their stuff. But I kind of like this notation because it shows, in my mind, the similarity in structure of the two. So, the difference being that this line, is a real number, b greater than 0 encompasses all real numbers, whereas in the previous notation, I was saying that cache c had to be a, positive integer. But yes, this delta model has a P sub I, the encounter probability, and the R sub I, or the expected positive catch rate. And both of those I'm gonna give this sort of big linear predictor that, and again, that we looked at the index model before, it's sort of similar structure, except now we've got two components. It's a delta model, so it's got the two components. And it still has the intercept that's independent among years, a spatial effect, a spatial temporal effect that's independent among years. And then it has this X, has this X thing that's a density covariance. So you might want to fit a model, a GLIM, where you've got measured, like if we're doing corals, we might think, pretty strongly that corals are going to associate with rocky habitat. And so on the West Coast, we've got this gold figure map for sandy versus muddy versus rocky habitat. You might put that in as an indicator variable, where you estimate sort of an average relationship of increased coral densities in rocky habitat. You might, like Ole Shelton and his EFH stuff, put distance from nearest rocky habitat in as a continuous valued variable for X. And then we've also got this separate variable that I'm calling Q, that I'll call catchability covariance. And this is indexed by I, sample I, and then there's multiple columns. And then catchability covariance could represent things that affect expected catch rates that are not spatially referenced and are therefore things, well, anything related to that, gear performance that you don't think reflects densities. So for instance, Ian Stewart had some paper about basically heavy, water state. And it makes sense if you're doing a bottom trawl and you start getting swells that are about 6 feet. It kicks the boat up, which tugs the head rope up, which means that the trawl is not sitting on bottom. And so if you're trying to get rockfish, suddenly, wave height is going to be a good predictor of density. But it's not something that's, it's not like wave height is driving density of fish 100 meters down. It's pretty easy to say that that will be independent of density of fish 100 meters down. So that's a good variable to think about as affecting catch rate, but not density that we put in as a catchability covariate. So we've got a linear predictor for encounter probability, that's logit linked linear predictor. We've got a log linear predictor with just all the same parameters and same structure for looking at log expected catch rates. We fit the model. We predict density across space, where we drop the non-spatial terms, we drop the catchability covariates. Like John said, we're kind of filtering out those effects. So we predict density across space and time using the same variables, but dropping the filtered out variables. And then how do you want to predict density in unmodeled locations? Well, I'm gonna always be using sort of some form of predictive process model because I'm kind of lazy. So essentially you model density at a set of locations S. Like if you've got a domain that represents the West Coast, you might model density at 100 locations at the West Coast. And then a predictive process model is saying you can predict density at any location by interpolation, essentially. So you can interpolate, a 0th order interpolation is just saying that you've got a piecewise constant function. And that's what I'm always showing here, where at a certain grain size, the model assumes that densities are constant. So it's saying the best prediction of density is equal to the predicted density of the nearest location that you're modeling, which I call a KNOT, K-N-O-T. Like here, this kind of dark blue is sort of a homogeneous prediction of density because I'm doing a predictive process model essentially that's interpolating densities as being constant at some fine resolution. INLA does first order interpolation using these piecewise linear interpolation between vertices of the SPDE mesh that we saw in the lab last week. And other people do higher order interpolation. But I don't because it's computationally expensive and I don't think the models do that well at predicting fine scales anyway. think this is there's 2 more slides, then we can look at the code. Once we've predicted density across space and time, there's kind of this laundry list of things that we can predict from that density function. So, historically, people only extracted the total abundance, which really I should, for consistency with earlier, I'll call B. So total abundance across space being, if you're using 0th order interpolation, all you need to do to calculate that is it's the weighted sum of model density, where each location that you modeled is weighted by the area that's closest to that spot. And so that's essentially an integral across space, assuming that you have a predictive process that's constant in the vicinity of each model location. So if you do this 0th order interpolation, it's really easy to do an integral across your density function. It's just a summation. You can also do the center of gravity. So there's these measures where x of s could be like kilometers north of the equator, and you model the average location of the population. So it's the weighted average of location for each model location weighted by the density that you're predicting at each location. And so Malin and William Chung think that we've observed evidence that species are shifting in the direction of climate velocities. I'm sort of skeptical because I think there's a lot of interannual variability that people have not really characterized very well. But you can model center of gravity this way. You can also calculate average density as the weighted average of density. So this is essentially like a measure of what's, intraspecific competition, what's the biomass, the average biomass around every individual. And then you can calculate effective area occupied as just the biomass divided by average density. So if you do dimensional analysis, this comes out as a measure of area. And this is a measure essentially of area expansion or contraction. So looking at habitat selection, density and habitat selection, and whether, there's some, I've kind of, me and others have claimed that there's evidence that as populations expand in abundance, they also spill out into suboptimal habitats. Any questions about these? I mean, there's kind of a whole long list of stuff you can calculate once you have the density function. And a lot of it's more interesting, I think, than total abundance.
Wait, what did you say that William and Malin were talking about with the center of gravity?
Yeah, so Malin, I think, he had a 2013 paper with Silovan and others about distributions shifting in the direction of climate velocity.
Oh, yeah.
But on the West Coast, he kind of concluded that things were shifting south, and I kind of that rebuttal paper with him where we kind of concluded that was not the case on the West Coast. I think there's a lot more to do about with center of gravity modeling. And then finally, maybe this one we'll come back to after everybody's gone through the materials last week. So there's some stuff about the SPDE method that I don't know if we covered last week. So we can come back to that. So does any questions before we look at the code? Or yeah.
I'm still confused on what the difference between the delta model and the zero inflated model are.
Yeah, so the zero adjusted model is essentially identical to a delta model, except a delta model has continuous support, continuous positive support, whereas a zero adjusted model has just discrete positive support. So they both have a mass of density at 0, and they both have a function that generates the predictions that are non-zero.
Yeah.
But they differ in the support of that second function.
So one doesn't have the
one of them's for counts, so counts will only be integer valued, whereas the other one's for biomass. Is there a different way you want to describe it, John, or anybody? Okay, so the index standardization model here we've got a function for simulating data that I'm not gonna look at, but, names, sim, let's see. Head, yes. So df for data frame has a location, the not number for 100 different modeled locations, 1 through 100, 10 years, so t sub I running from 0 to 10, and then a true log density at that not, just to record it, so I can look at it later, and then a simulated count, probably from a Poisson distribution in each location. So this is just the data frame of survey counts, like if we've done AUV samples for coral. We then, to fit it, we generate this mesh, this SPE mesh that we talked about last week, where we put a triangle vertex at the location of every datum and model adjacency by connecting those vertices with triangles. We use inlet to generate this SPDE object that has SPDE, I forget what the slot is. I'll see it in a second. And then I want to calculate the area associated with each modeled location. So I generate a vector of areas. And I do that by making this extrapolation grid that's finer than this arbitrarily fine scale. So in this case, I overlay a grid of 1,000 by 1,000. I use a k-means algorithm to figure out how many of those 1,000 by 1,000 or those million grid cells is closest to each location. And I say that number is, a good approximation of the area that's closest to each model location. Does that make sense? It's a way of.
So the units of area, there aren't really any.
Well, so because it's 1,000 by 1,000 cell and I'm overlaying it on a 1 by 1 grid. So I don't really, I'm not writing out units, but let's pretend it's a sample that occurred over 1 kilometer by 1 kilometer. And I generate a 1,000 by 1,000 grid. Each grid cell has 1 meter by 1 meter, I guess. So you can work out what the area is. It's just hard to do in this example because I didn't declare any units or anything. I load the TMB object, and let's look at that in a bit. The params, there's, for some reason, I guess I've just got an intercept that's constant across time, which is kind of annoying. If I'd gone back, I would have done that more like the index model that I've been talking about. But params includes epsilon st, which is the space by time matrix. And as you'd see in the SPE in the lab last week, it has 116 locations because it's got 100 model locations plus an additional 16 that kind of border the domain to deal with boundary effects. Tau is a measure, is essentially the standard deviation. It's what controls the standard deviation of omega, which is the spatial effect, or tau epsilon for the spatial temporal effect. Kappa controls that's the decorrelation rate. And then omega s is the spatial effect, or it's the spatial effect, so it'll be 116. So in these parameters, we've got a spatial standard deviation, a spatial temporal standard deviation, a decorrelation rate. It's the same between those two, the way I set it up. A spatial effect, a spatial temporal effect, and a global intercept, which I probably, like I said, I should have had be, a factor, a separate for every year to fit with the notation I've used elsewhere. So I'm going to run this model, and while I'm running it, I'll just walk through. The new thing here is this bias correct equals true, and in the lab last week, Jay, I think there are slides about bias correction, am I right?
Yep.
So this bias correction is dealing with retransformation bias. So we're doing all the random effects in log space or logit space. And so that smoother is gonna be biased once you apply a nonlinear transformation to it. And that bias, this epsilon bias correction estimator is a way of bias correcting that transformation bias. That's the short summary for people that missed it last week. So if I run it, I do one Newton step just to drill the solution in, I get the standard deviation. And all of the final gradients look fine, the maximum gradient, there's no NAs and the standard errors, so it looks converged. And then finally, you can pull out the covariance out of the opt-SD slot. So opt-SD, you can look at the reported variables. And I'm reporting out, I should have called it lowercase b sub t, so I'll probably change that in a second here. So the total abundance for every year is estimated on the left-hand side. And we can look at how well that actually did, I guess, just a second. Sim list. So I can plot x equals sim list et, y equals opt sd. So I'm plotting the true on the x-axis versus the estimated on the y, and it looks plausible that there's some proportionality constant between the two, so it's a good index, even though the scale is different. I suppose the better way to show that would be T. Any questions while I'm doing this?
I had a question, but we could probably wait until we look at the TDP script about kappa versus rho. I'm guessing it like achieves the same thing. I don't know.
Totally. Let's look at that in a second.
Okay.
So, geez.
And what's going on with, I'm looking at this nearest neighbor bit again, this area for each location.
Yeah, so go on.
So we we have X and Y locations for our data, then we create this big old grid and find the nearest neighbor across the grid scale cells,
Yeah.
assuming, and then calculate the distance between those nearest neighbors.
Yeah, so divided by. So the point is that we're using this predictive process model. We want to approximate a density that's defined over this square domain from 0 to 1 and 0 to 1.
Mhm.
We want to predict density at any location in that function. And we never really want to deal directly with that function itself. Instead, we want to deal with points in that function and approximate it. And so, we choose 100 locations to model in that domain, and then we interpolate any other location using a 0th order interpolation. So we say any location that's closest to a given knot has the same value as the closest knot. So then the question is, how big of an area is associated with each knot? And there's a bunch of ways you could do that. One of them is you could start randomly drawing locations from one-to-one domain, like using R-unit statements, and do that 1,000,000 times or 100 million, and calculate the proportion of them that are closest to a given cell. And so that would be like a Monte Carlo way of calculating that problem. But it's more efficient to do a uniform grid in this case, so you can show that the error in the calculation of A sub s for a given sample size is lower doing it this way than doing the uniform Monte Carlo simulation. is that we want some quick and dirty way of like approximating the area associated with each model location.
Gotcha.
Okay, so finally I got that plot set up where the black is the true abundance in each year. The red is the estimated total relative abundance in each year, and they look like they match. I mean, it's plausible that there's no bug. And then if you look at the correlation matrix, I can extract the covariance matrix using this slot cove from the standard deviation object. And if I translate that cove, that covariance looks like this, which is kind of hard to read, but I can use the cove to core function to translate it to a correlation matrix. And this correlation matrix, it's 1 on the diagonal, and it's 10 by 10 because there's 10 years, and it shows that the covariance between years, the off diagonals are all less than 0.01. So, I've designed the model to have minimal covariance between years, and in fact, it does have that property. It's a little silly. I should have looked at this slightly closer before I put that in grid. So on the C++ side, I'm always going to have this is NA thing at the top so that I can just put in, I can, like we did in that homework, you can put in if you do a cross-validation experiment by just replacing 10% of the data with NAs and summarizing the predictive probability of those left out data if you wanted. Anyway, so that's what I've got is NA there. All of this should look familiar, where I'm reading in the number of locations, the number of years, the area associated with each location, the data, the space and time associated with each observation, and then this SPDE stuff is the stuff that's new from as of last week. So M0 is this thing that's generated by INLA, where if I plot M0, it's just a diagonal matrix. M1 is the first order adjacency matrix of that SPDE mesh. And M2 is the second order adjacency of that SPDE mesh. So, like for instance, new, if I can show that it's the second order adjacency by just taking M1 times itself, and it'll have the same structure. So this is M1 times itself, and this is M2, and they have the same structure. So that's sort of the easy way to confirm that M2 is the second order adjacency matrix.
That's of the data points, not including your predicted locations.
Yeah, well, it's specifically, it's the locations of this mesh. So the mesh has, and this mesh, in this case, there's a mesh vertex at every data point, plus these additional 18 on the outside. In INLA, you can configure it to do a bunch of different stuff. So you could have fewer mesh locations than the number of data or more or whatever. So it's the adjacency of those 118 vertices on this triangle, where it's adjacent if they share a triangle, and otherwise not. And again, that's stuff from last lab, and I'm happy to come back to it at the lab on Thursday. But we're kind of running, well, we're out of time technically. Are people okay staying for another couple minutes? So this M0, M1, M2 are passed as these data sparse matrices, kind of like we started seeing in week 5, I think. I've got the list of parameters we looked at, some of which are a vector and array. I load in this using namespace density because I'm going to do this using the built-in functions TND, and then there's this bookkeeping that we're used to seeing. In the PowerPoint, I glossed over one slide where we show how to calculate the range, the distance at which correlations are 13% or about 10% is defined as the square root of 8 divided by kappa. So that's just from the paper that derived the SPE method. There's no intuition to that particularly, it's just the formula that you need to use. And the marginal standard deviation is equal to tau, 1 divided by tau times kappa times the square root of 4 pi. So again, that's just straight from the paper. And so I'm just putting those formula in here to calculate the range and the sigma O, sigma E. This SPE method then calculates the precision of the random effect as this sum of those 3 sparse matrices and this parameter log kappa. So it's technically kappa to the 4th power times m0 plus kappa squared times m1 plus m2 is the formula for the precision matrix of a Gaussian Markov random field. And I can implement that for the spatiotemporal, well, for the spatial smoother, I can take that precision matrix and put it into the GMRF function, and that returns a function that would calculate the negative log likelihood for a field with standard deviation of, well, it's a little complicated. You have to rescale it to be this log tau to get it to have this standard deviation. So this is sort of a little bit confusing, and I don't want to spend the time right now to walk through the logic of it. But this function says that omega, the spatial effect, follows a spatial process with a decorrelation rate controlled by kappa with range equal to that calculation up there, and with standard deviation controlled by log tau O with standard deviation according to that formula up there.
I like just syntax wise, why is there not like a asterisk in between like where the scale parentheses ends and the omega parentheses begin? Are you multiplying those two things or like?
No, so we started seeing this syntax in week 5.
Yeah.
I thought of it last time, and basically the point is that this function has just one input and it returns a function. And so you can do this one and return a function. And then to call it, you have to do another parenthesis with the vector you want.
Okay.
So you can do GMRFQ and then just this parenthesis, and that would be valid. But the problem is the scale would be wrong. And so you put this GMRF in a function called a scale, and that returns a function, and then you apply it omega s.
Okay, that's clear.
Yeah. And the reason that they do this syntax is that it can save, for big models, you could save the function that's generated by this call, save it as an object, and you wouldn't have to construct it multiple times. It just saves a little bit of computational overhead if you want to get really fancy with your coding. And then for the spatiotemporal term, I just loop through the columns of this matrix epsilon st, and each vector that I extract has that same spatial process, but with a different log tau. And then I calculate true log abundance or log density as using the linear predictor. And then I fit a Poisson model where I exponentiate that linear predictor and have that as the intensity function. So then the joint negative log likelihood is the sum of the negative log likelihood for the spatial process, the spatiotemporal process, and the data. And then I calculate total density, expanding it up to area associated with each location, call that d sub s, and I'm just gonna edit that to be, or b, I'm gonna edit that notation so that it matches the notation from the PowerPoint. Yeah, so that's the entire code. So the point is you can do a spatiotemporal index model in under 100 lines where almost all of this is either bookkeeping input or output. And the workhorse functions, one of them is this probability of the data, which follows just kind of standard R syntax when it comes down to it. And so really the only complicated thing in a spatiotemporal model is this block of 5 lines. It's, pretty compressed code, so it's hard, I'm trying to help people get familiar with what these mean, and I'm sorry for people that missed last week, because it probably does not seem comfortable. But, in the end, this is pretty easy to skim, and so you can build up more complicated models while keeping code that you can read for bugs by eye. Okay, so we're out of time. Thanks everyone for sticking around a little bit. Any last? Feel free to stick around if you want to ask me questions. I'll be here for a few minutes.
Thanks, Jim.
Thanks.
What's the double colon, eigen colon sparse matrix?